my worst error was never, as far as I know, spotted by Sidney. It was an article on the Kondo problem, where I neglected to explain the very simple limit of the Kondo problem, which I used myself to understand what was going on. So I hope that subsequent generations of researchers will look to Sidney to learn how to do review articles right and continue his glorious tradition. Well, it's my privilege to introduce Stephen Weinberg, who is an overarching figure in high-energy physics. He has a much-deserved Nobel Award. He pushed very hard on the gauge theory of weak interactions before that was generally popular. He's produced soft Pion theorems, and he has helped everybody with the books that he has written, which are as useful for professionals like us as for the lay public. So it's my great pleasure to introduce Stephen Weinberg, who will be talking on cosmological correlations. Steve?
Thank you, Ken. I first met Sidney in 1964 at the Rochester conference that was held that year at Dubna that Shelley mentioned. I was sitting on a stone bench looking at the Volga River, and a young man came and sat next to me and turned to me and said, "Hello, I'm Coleman." And I didn't have any way to top this bit of repartee. So I said, "I'm Weinberg," and I still have never been able to top Sidney. He has said so many things that have stuck in my mind, remarkable sayings of his. I remember when he was elected to the National Academy of Sciences, he broke out in a smile and said, "I've always wanted to be an old fart." And in a more serious vein, he once said contemplatively, "If we can see farther than those who have gone before us, it is because we have stood behind the shoulders of dwarves." Well, these are remarks that you might think Sidney could have prepared in advance. But what I think really impressive was something that happened in the gauge seminar. I'm so glad Ken Lane mentioned our old gauge seminar that met in the faculty room on the third floor of Lyman when Ken spoke last night, because it reminded me of this, which I think is Sidney really at his most characteristic. He was giving a talk at the gauge seminar, and it was a very crowded room, which is one of the nice things about it. And Shelley Glashow was there, and Shelley fell asleep. And I don't think it was a reaction to Sidney's talk. I think he had been up late the night before or something. But anyway, Shelley was sleeping actually quite nicely. And Sidney tried to soldier on, but I could see Sidney was getting annoyed. And at a certain point in his talk, Sidney suddenly stopped. And he looked at Shelley, and he said, "That's very interesting. That's stage 3 sleep, indistinguishable from clinical death." And at this point, Shelley woke up, and he heard everyone laughing, and he was a little puzzled what was going on. And Sidney then topped himself and said, "In all but 10 states, you could take out his heart." Well, I never had the pleasure of collaborating on an article with Sidney, but I was here at Harvard in the great decade of the 1970s. I was here from 72 to 82, and the place was tremendously exciting then, and very largely due to Sidney, as well as a couple of other characters like Shelley Glashow and Howard Georgi, and a remarkable variety of young postdocs and students and junior fellows. And it was, as we all remember, a golden age for theoretical physics, particle physics, something that we haven't seen in our field for a while. I don't know, other people, when they refer to the 70s, remember Watergate and high unemployment combined with inflation, but I remember that as most wonderful period in physics, and Sidney's presence here is a large part of my memory of that. Now I think it's cosmology that is in a golden age. For the last 15 years or so, it reminds me of what particle physics was like then, with a wonderful fusion of progress in theory and experiment relevant to each other. And so I want to talk about, since this is a conference on quantum field theory and QCD, I'm going to talk about quantum field theory with an emphasis on the quantum in cosmology. Since 1992, I think it's fair to say that the most exciting things that have been going on in cosmology, with the possible exception of the discovery of the accelerating expansion, have been in the area of studying the fluctuations away from the smooth Robertson-Walker expanding universe. Of course, astronomers have always been interested in the fluctuations. I mean, after all, what else are stars and galaxies? But stars and galaxies of fluctuations that have evidently gone beyond first-order perturbation theory. They are in the nonlinear regime, and so it's very difficult looking at them to learn things about the very early universe. But in looking at the cosmic microwave background, which we've been doing, looking at the fluctuations in the cosmic microwave background, which we've been able to do since the COBE satellite in 1992, and now increasingly with very large surveys of interstellar matter at large redshifts before it becomes nonlinear, I should say intergalactic matter at large redshifts, we're beginning to really have experimental data on fluctuations in the universe that ties in with theories of the early universe. Now, this, at first sight, is very surprising because we have theories of we have paradigmatic theories of the early universe, starting with the work of Alan Guth under the general heading of inflation. And we have our measurements of things that happened when the universe was a few 100,000 years old, which is what we see in the microwave background. But in between those two eras, there are a lot of things we don't understand at all. And how is it that we can interpret what happened in the very early universe in terms of things that happened when the universe was 380,000 years old? When there's so many things that happened in between we don't understand. And the reason is that during most of the history of the universe, from well before the end of inflation, and here's my first U-graph, until relatively recently, by relatively recently I mean after nucleosynthesis and electron-positron annihilation at temperatures well below 10 to the 10th Kelvin, all the fluctuations that we actually observe had physical wavelengths that were outside the horizon, in the sense that the co-moving wave number, which is Q over A, where A is the Robertson-Walker scale factor, it's the thing that tells you how the universe is expanding, is much less than H, the expansion rate, A dot over A. And here is a figure, Q over A, during inflation, when A is increasing exponentially, decreases exponentially, and then after inflation, A increases like about T to the half or T to the 2/3, so Q over A decreases more gently. On the other hand, the Hubble rate, H, during inflation is roughly constant. That's what makes inflation. You have an exponential expansion. And then after the end of inflation, h decreases essentially like 1 over t, which is faster than q over a. So you have an early period when fluctuations are inside the horizon, and then they leave the horizon, and then for a long time they're, for a long time, even by our standards, they're outside the horizon, and then eventually they re-enter the horizon. Now, it's during that period when they're outside the horizon that all the things happen that we don't understand. The energy that was in the inflaton fields gets converted into ordinary matter and radiation in an era called the era of reheating. Baryons are synthesized, we think. The cold dark matter gets decoupled from other matter and radiation. There's the Rick era that Frank Wilczek talked about, when the chiral symmetries get broken. None of these do we actually need to understand if we want to calculate the fluctuations that we will see now, because they all happened at times when the wavelengths of those fluctuations were outside the horizon. I'm sometimes amused by the statement that was often made when people were arguing for the Rick accelerator, that it was needed to recreate conditions in the early universe. And that's true in a sense, but it's also true that we don't need to know any of that. Now, the reason why I emphasize so much that these fluctuations were outside the horizon during this era is that there are conservation laws that apply when fluctuations are outside the horizon. In particular, there's a certain linear combination of perturbations. Psi is a half the coefficient of the unit matrix in the perturbation to the space part of the metric tensor, and delta U is the velocity potential, which appears in the energy momentum tensor. And I think Jim Bardeen was the first person who wrote down this linear combination. One can prove, and this is recent work of mine, one can prove that whatever the constituents of the universe, whatever is going on, there is always one mode, which, in fact, there are two, but the other one decays rapidly. There is always one non-decaying mode where R is constant. It's called the adiabatic mode because in addition to R being constant, the fractional density perturbations for each constituent of the universe, delta rho is the perturbation in the energy density, rho bar plus p bar is the unperturbed value of the energy density plus the pressure. Delta rho over rho bar plus p bar is the same for photons and cold dark matter and everything. Everything, whatever it was, during this period when the fluctuations were outside the horizon, all had the same value for that quantity. And this, by the way, is confirmed, although not with high accuracy yet, and it remains to be confirmed with better accuracy by observations of the microwave background. When you study it, the microwave background, the standard model assumes that this is true, and that's what works. Now, in general, there are other modes where R is not conserved, but there are two situations we know of in which R is conserved, and the universe must be in this adiabatic mode. One is single field inflation, inflation driven by the energy of a single inflaton field. And the other is if the universe ever spent a sufficiently long time in a state of thermal equilibrium with no non-zero values for conserved quantities, as we think must have been true before the baryons were synthesized, then the universe is forced into an adiabatic mode, and even though those conditions no longer remain valid afterwards, I mean, eventually the cold dark matter decouples. It's not in thermal equilibrium anymore with the rest of the universe. You begin to have non-zero conserved quantum numbers like baryon number. Once you're in the adiabatic mode, because it is a solution of the equations, whatever the constituents of the universe, it remains a solution. You might wonder how you can prove something like this without knowing anything. And the reason is this is essentially a Goldstone theorem. The reason that you can prove this is because there is a symmetry of the field equations, which is not a symmetry of the unbroken, unperturbed solution. And that's the classic situation which leads to a Goldstone mode. The fact that this is constant is because time, well, it's the same thing as saying that the Goldstone boson only appears, the field only appears multiplied by derivatives. This is what are called scalar modes, that is, modes which are rotational scalars, where the degrees of freedom are rotationally invariant. There's also a tensor mode, and the same theorem proves that there's also a tensor mode for which the gravitational wave amplitude is conserved outside the horizon. There's another mode, but it decays rapidly. So we have these conservation laws. Now, once the perturbations re-enter the horizon at this relatively recent era, which, well, it depends what their wavelength is, but for some of them, it's just before the recombination of hydrogen when the universe is 380,000 years old. For some of them, it's more recently. Some of them haven't re-entered the horizon yet. But when the perturbations re-enter the horizon down here, that's sufficiently late so that we do understand the physics from then on, and we can calculate what happens. It's complicated, and you get all these acoustic vibrations, and you see these beautiful pictures that come out of the MAP satellite showing the multipole structure as a function of CL versus L, and this complicated structure is produced by these acoustic oscillations. You see, you don't need PowerPoint. But this is really a very nice morning. 2 talks given by Weinberg, neither using PowerPoint. We understand the physics of that. So all you need in order to calculate what we see are what the correlation functions of the perturbations were while they were still outside the horizon. And this is the typical object that the quantum field theorist is asked to calculate. The average value of the product of scalar perturbations, the script R, and gravitational wave perturbations, perhaps, at different points in space, but at a time which is not indicated. The O means outside the horizon. Given that, that's the initial condition for calculations when the perturbations come inside the horizon, which are quite complicated, but where the physics is completely well understood. Well, we think it's completely well understood. The successful calculations, which are shown by the agreement of theory and experiment for curves like this, the successful calculations that have been done so far make 2 large assumptions. One is that the fluctuations outside the horizon are Gaussian, which means that all those correlation functions can be written as products of binary correlation functions, sums of products of binary correlation functions. And the other is that they're linear perturbations, and in particular, if they arise in slow roll inflation, then as first shown by Guth and P and Starobinsky and Hawking independently, the Fourier transform of the binary correlation function, which is all you need, goes like simply a power. Well, it goes approximately like a power, but for slow roll inflation, that means that the energy of the inflaton field is only gradually decreasing. You get a spectrum which is very close to q to the minus 3. It is really 1 over f noise, in other words. And the coefficients, the actual power, which is not precisely minus 3, and the constant in front depend only on the details of the expansion at the time the fluctuation left the horizon. In other words, to calculate the constant factor big N and the exponent little n, all you need to know is what was going on around this time when the fluctuations left the horizon. The whole, I mean, there were at least 60 e-foldings of expansion, probably many more. We don't need to know anything about that. We just need to know what was going on there. Well, of course, that's good in the sense that we can do calculations and hope to understand what we observe, but it's bad in the sense that we're not really learning very much about the whole history of inflation. This assumption of Gaussian correlations is the analog of what we would do in quantum field theory if we took a 4-point function and wrote it, well, for example, for the 4-point correlation function, if we wrote it just in terms of Feynman diagrams, where we had lines, bare lines, simply passing through the diagram. And the second assumption, that we treat this as a linear perturbation, means we get these propagators just by solving the classical field equations without worrying about quantum corrections. Now, one can do better than that. One can consider the possibility of non-Gaussian fluctuations. This has become quite interesting lately because the experiments are getting good enough to look for these. So far, they've been mostly calculated by solving the classical field equations beyond the linear approximation. This corresponds, and in particular, a calculation done by Maldacena a few years ago calculated the 3-point correlation. Well, this corresponds to just using the tree approximation, if I make an analogy with Feynman graphs, but these are not Feynman graphs. And in fact, what kind of graphs they are is in a way, the point of my talk. This may look like an easy calculation, but it's not that easy. This is what practical cosmologists call the bispectrum, because it depends on 2 independent 3 momenta rather than just 1, as you do have for the 2-point function. And again, Maldacena found that the results of the calculation, the non-Gaussian, in the Gaussian approximation, of course, there is no correlation of 3 things because you have to correlate them in pairs. Well, this 3-point correlation, the bispectrum, turns out in Maldacena's calculation, again, to only depend on details of the expansion near the point of horizon exit. So I thought I would try, having an old fondness for quantum field theory and a renewed interest in cosmology, to look and see what quantum field theory could say to go beyond the classical approximation and include things analogous to loop diagrams. And in particular, I was interested in the question, which is a somewhat practical question. Well, of course, the question, how do you calculate things like this? And second, will the results depend only on the details of the expansion at the time of horizon exit? Or is this something that for the first time may depend on the whole history of inflation? Now, this problem, now getting into the more technical part of my talk, which is, let's see, I started at 11:15. Is that Arthur? Arthur, there you are. When did I start?
I don't know.
What does it say on the schedule?
It's on the schedule 11.
Okay, all right, fine. Then my talk is about half over. No, well, a little bit more than half. This problem is different from the kind of problems that we all learned about in the 70s when we were doing quantum field theory here in 2 important ways. One is, of course, it's a time-dependent problem. And I think it's important to be careful about how the time dependence gets into the problem. The problem, after all, has a time-independent Hamiltonian. The Hamiltonian is the Hamiltonian of gravity and matter fields. It's the Hamiltonian. It's time-independent. And it generates the time dependence of the fields and their canonical conjugates. Here, this is a very condensed notation. Phi A runs over all the matter and gravitational fields with A labeling which you're talking about. Each of these can be written as a time-dependent, unperturbed value plus a fluctuation. And this Hamiltonian, although it generates the time dependence of the fields and conjugates, does not generate the time dependence of the fluctuations, in the sense that the commutator of H with the delta phi times I is not delta phi dot. In fact, what it is it's phi dot, because the unperturbed phi, of course, is just a C number and commutes with H. The Hamiltonian, the correct Hamiltonian to use, the one that generates the time dependence of the fluctuations, is given by expanding the Hamiltonian around the unperturbed solution and throwing away the linear terms. Here's the unperturbed Hamiltonian written in terms of the unperturbed canonical variables, the terms of first order and fluctuations, and then second and all higher orders. And it's very easy to see, just using the canonical commutation relations, that it's the H tilde, the term where you've thrown away the first order and the zeroth order terms, whose commutator with the fluctuations gives you the rate of change of the fluctuations. The second point is slightly less trivial. What we know is what happens for t equal minus infinity, because that's when the fluctuations are deep inside the horizon, and the universe then the de Sitter metric becomes almost irrelevant to the quantum fields. The universe looks like it's expanding very slowly. Q over A is much larger than H. And so our initial condition is that the fields, the fluctuations, go to free fields at t equal minus infinity. We're in a vacuum which we understand what it looks like at t equal minus infinity. We're in what's called the in vacuum. That is a vacuum that in which the fields behave as free fields at t equal minus infinity. We don't know what they behave like at t equal plus infinity. So when we calculate correlation functions, we don't want to calculate what you usually calculate in quantum field theory, which is the matrix element between an in state and an out state of a product. In quantum field theory, it doesn't matter because the out vacuum is just a phase factor times the in vacuum. But that's not true here. The out vacuum, which looks like a vacuum at t equal plus infinity, is completely unrelated to the in vacuum, because the universe in between is evolving. And so what we want is an in expectation value. Now that's precisely what Schwinger, many years ago, developed a formalism for calculating. It's called the in formalism for obvious reasons. And the prescription is that you take, to calculate what you want, you take an anti-time ordered product. Well, first you expand the Hamiltonian in terms of an unperturbed Hamiltonian, which is time dependent plus an interaction. You rewrite everything in terms of interaction picture fields, which are free fields with time dependence given by the unperturbed time dependent Hamiltonian. And then you write a infinite power series, anti-time ordered, times the things you're taking the expectation value of, times a time-ordered exponential power series, and that gives you the in expectation value. This formula, you see, in ordinary quantum field theory, where you calculate the out-in expectation value, what you would do, you would have a single time. Oops, that's not a good view pen. You would have a single time-ordered product of the things you're interested in and an exponential e to the minus I L dt. Well, that's not what you have here. You have an anti-time ordered product, a product, and then a time-ordered product. Maldacena, in his calculation, didn't have to do this. In fact, didn't even write it correctly at first, because he but it didn't matter because the time ordering and the anti-time ordering didn't matter because he just worked to first order in HI. So to first order in HI, it doesn't matter whether this is anti-time ordered or time ordered or what. But if you go to second or higher order, you do have to worry about this. Now this leads to a graphical interpretation. You have not Feynman diagrams, but diagrams with two kinds of vertices. You have left vertices, which come from this anti-time ordered product, right vertices, which come from this time ordered product, and three kinds of propagators. Those which connect two left vertices, a left vertex, and a right that propagator is an anti-time ordered product. Two right vertices, the propagator is the usual Feynman propagator, and a left vertex and a right vertex, in which case the propagator is just an ordinary Whiteman function. From this operator formalism, you can derive the path integral formalism, and now you have to do path integrals over two different kinds of fields and their conjugates, left fields and right fields. And you have two different integrals, and the integrals are tied together by conditions that say that at the time t where you're evaluating the expectation value, at this time t, which for us is any time outside the horizon, the left fields have to equal the right fields, and likewise for their conjugates. And then you have to put in the vacuum wave function at t equal minus infinity, where the Lagrangian is the usual Lagrangian, but with the momentum not yet integrated out. Now, you can use this path integral formalism for all sorts of things, and one of the things that I've used it for is to prove, using tricks I learned from Sidney Coleman, actually, but in this slightly different context, the theorem that says that if you do what the cosmologists, the working cosmologists have been doing up till now, which is just solve the classical field equations and impose the condition that at t equal minus infinity, the fields go to free fields with well-known expansions in terms of creation and annihilation operators, that all you're doing is evaluating the sum of tree graphs. And that's I think, the trick is you put in a fictitious coupling constant and you let it go to 0, and when it goes to 0, it picks out the classical path, and it also, by simple power counting arguments, you can show that that's what gives you the terms with 0 loops. I won't go through the details of that. This in formalism of Schwinger has had some practical, well, it has been applied in cosmology, but not with the kind of practical application that I have in mind. For the work that I've done, I find it actually more convenient not to use this rather complicated graphical formalism, but instead to use an equivalent formula where instead of writing anti-time ordered products and time ordered products, you have a single formula in terms of nested repeated commutators with the latest time commutator on the inside, and then the next to latest, and then the last commutator you take is for the earliest time. And that gives you the same result. The reason this is more convenient is if you use the Schwinger formalism, you find all kinds of cancellations. In fact, I was puzzled by that for a while because a lot of things just canceled, and it turns out they all cancel because of the fact that all you're doing is evaluating commutators. So I recommend this formula. Now, I wanted to just do a warm-up exercise, so I considered the case of inflation with one inflaton field plus many matter fields. After all, we mustn't forget that even in simple single-field inflation, where only one field has an energy, has a vacuum expectation value with an energy that drives the inflation, all those other fields are still there. As Eric Weinberg said, you know, quantum field theory was there in the past, and whatever fields there are were there. I mean, I guess once we're in the effective theory that represents string theory in R4 space-time dimensions, it's very convenient to deal with this single-field inflation in a gauge used by Maldacena, where you choose the coordinate system to follow the variations in the inflaton field so that there are no variations in the inflaton field. You just define the time slices so that the inflaton field is always just equal to its unperturbed value at that time. And then all of the physics goes into the metric. And in terms of the quantity R and gamma, the scalar and tensor mode, at least the first order, the metric is then given by these somewhat complicated looking formulas, but they're just formulas in terms of the perturbations R and gamma. H is our old friend, the Hubble expansion rate. Epsilon is minus h dot over h squared. It's the thing that has to be small and positive during inflation. It has to be small during slow roll inflation, which is what we assume in order to get the right spectrum. Maldaceno's tree calculation, as I said, is just the calculation of that diagram, and I redid it. And you can easily see why he got the result he did, that the answer only depends on what happens at the time of horizon exit. The interaction is essentially, in this gauge that he used, essentially just an integral of r dot squared times the inverse Laplacian of r dot. The important thing is that there are 3 time derivatives. And if you calculate the integral, remember you have to do an integral over the time of this vertex. This vertex is labeled with an x and a t, and you have to integrate over the time. The integral going down to t equal minus infinity, long before a horizon exit, is suppressed just by the fact that r is rapidly oscillating. You're deep inside the horizon. The fields are oscillating rapidly. That kills the integral. When t goes to infinity, meaning in this context just any time long after horizon exit, r is going to a constant. In fact, it's going like r dot is going like 1 over a squared. Well, you've got 1 over a squared, 1 over a squared, 1 over a squared. That's 1 over a to the 6th. That's more than enough to cancel this a to the 5th, and the integral converges like the integral dt over a. And so both late time and early time are suppressed, and the only time that matters is near horizon exit. Now, for loop calculations, I've only so far looked at matter loops for 2 reasons. One is that they actually dominate. They don't dominate because of counting powers of 8 pi g. In a theory where matter only interacts gravitationally, and gravity interacts with itself, of course, gravitationally, you can show that, and I do that here, that the number of powers of 8 pi g is essentially just determined by the number of loops, whatever kind of loops they are. And all loops, therefore, contribute a factor which is essentially h pi g h squared, which is approximately 10 to the minus 10th, which makes this somewhat academic. The other good reason for only considering matter loops is it's also easier. But matter loops dominate. I'm sorry, I didn't finish the previous thought. Matter loops dominate because there are more matter fields than graviton fields. And if there are hundreds of matter fields, you pick up factors of hundreds. The interaction between matter and gravitation in this gauge, and I'm dropping the I now, meaning interaction picture. These are all interaction picture fields. Is just the integral of t mu nu delta g mu nu. I gave you a formula for what delta g mu nu is. You have to know the energy conservation condition, which is this one, and you have to know the field equation for R, for the free field R, and you put that into the interaction, and things get tremendously simplified, despite the great complexity of delta g mu nu, which convinces me that this must be the right way to do it, because everything cancels. And you're left with a very simple expression, again with an a to the 5th, in terms of a certain combination of the energy momentum tensor components, and a surface term, F, which I won't talk about. And for minimally coupled real massless scalars, this interaction just becomes a to the 5th times an integral of chi dot square inverse Laplacian r dot plus a surface term. And once again, you can, if you, for example, consider a one-loop diagram, you get diagrams like this. Once again, you can do the counting of powers of A. Once again, everything converges at times long before horizon exit because the fields are rapidly oscillating. And if you worry about what happens long after horizon exit, each vertex contributes a growing factor A to the fifth. That's this factor here and here. I should say here. Each factor r dot contributes an A to the minus 2, and the two factors of chi dot, chi is the matter field, contributes a factor A to the minus 4. So once again, each time integral converges during inflation, like the integral, just like the integral that gives you the conformal time. Now, I've actually done the calculation for a simple warm-up problem, which is just the two-point function, and I will spare you the details. And the final, there they are. And the final answer with a problem is just this, minus 11 pi, 8 pi g h square at the time of horizon exit square. I promise you that's what it would depend on, divided by 122 pi cubed, log q over q cubed. We only have one momentum in the problem because this is a two-point function. And then there are infinities. This integral that you see above is quartically divergent. And so you get a quartic polynomial. Well, you know, you shouldn't be surprised at that. After all, general relativity is a non-renormalizable theory. But we learned that the way to deal with infinities in non-renormalizable theories is renormalization. Non-renormalizable theories are just as renormalizable theories. You just have to put in enough free parameters. And the free parameters in this case are the cosmological constant itself, which gets accompanied with a quartic divergence, and the gravitational Newton's constant, which gets accompanied with a quadratic divergence, plus a term in this gauge, which is just an r square term, a curvature square term, which gets accompanied with a logarithmic divergence. Now, in flat space, we get rid of these divergences by putting in bare couplings which have infinities, which are so defined so that the renormalized couplings, the physical couplings, the observed cosmological constant and the observed Newton constant, and observe whatever this is constant, come out finite. If you go to higher loops, of course, you need more constants. I am assuming that if you do that in flat space, then the counter terms that appear when you do this calculation during slow roll inflation will serve the same purpose. And so I strongly suspect that this quartic polynomial just amounts to a constant factor, that the quartic divergence and the quadratic divergence are actually absent because they're canceled in this way, and that this what's left is a logarithmic divergence, which just gives you the unknown constant factor that goes in this logarithm, which corresponds to the unknown coupling of r square. But I haven't been able to prove that. And I'm running into technical difficulties actually with regularization, because what you do in flat space is so different from what you do when the universe is expanding. And my instinct at this point is to ask Sydney, and that's what I would do in happier times, because that's what I kept doing during those period of the 70s when I carried a calculation to a point where I began not to understand what I was doing. I would ask Sydney, this calculation has been done very much in the Coleman spirit, that is, with a factor 10 to the minus 10, even if you multiply by hundreds of types of matter fields, it's still going to be too small to be experimentally observable. But as Sydney always did, I think it's important not only to work out what theories predict for experiments that can be done, but really to understand what our theories mean. And it's in that spirit that I've been giving this talk, trying to understand what quantum field theory really means in this kind of context. As I said, if I could, if geography allowed it, I would have been asking Sydney about this all along. You know, Paul Steinhardt, I think it was, gave a talk yesterday in which he started out with a list of Sydney students. And my only criticism of his excellent talk was that I felt that I should have been included in that list. Because it is really literally true and not just an idle compliment. And I think many of us here can say this, that I have learned more about physics from Sidney Coleman than from anyone else I have ever known. Thank you. Oh, David has, no wonder you reminded me. That the past history doesn't affect?
Could you repeat the question?
Yeah, could you say it again? Here, let me stand next to you. Yeah. Only the time of horizon exit. Yeah. Yeah, that if it's true in zeroth order and it's true now in first and second order, we've always known it in zeroth order since Guth and P and other people, and now Maldacena showed it in first order and I've showed it in second order. Yes, except that because I've only worked to the order I've only had to work with this trilinear interaction. And in order to go beyond what I've done, I would really have to I'd have to write out the complete Lagrangian for gravity interacting with a matter field in this gauge and count the powers. And I should do that, yes. Well, this is work in progress, but I will. The graphical calculate part is not hard. It's simple power counting. But what I have to do is in this gauge where I've gotten rid of the fluctuations in the matter field, write out the complete interaction of gravity and matter and check that it always works out this way, which, as I said earlier, would be both good and bad. It's good because that means we can do these calculations for whatever they're worth, and bad in the sense that there seems to be some obstacle to our learning anything about inflation except what happened at horizon exit. Another question? Yes?
Usually in these problems of having like scalar fields and background gravity, you do adiabatic expansions to the modes, and you can identify what the divergent terms could be, r squared and r, and it just works out.
Well, except, yeah, the problem is, how do you do this? In flat space, for example, you might use a cutoff and write counter terms. I mean, that's the most naive thing you could do, but think of that. You could put in a cutoff, a brutal cutoff, and that means that you never integrate for wave numbers beyond a certain point. Now you want to do the calculations that I'm doing. Well, I'm not integrating over physical momenta. I'm integrating over co-moving wave numbers. Now, there's a simple relation between them. The physical wave number is the co-moving wave number divided by the Robertson-Walker scale factor. But at what time? There are many times in these diagrams. And I don't know how to convert from a cutoff in physical momenta to a cutoff in these co-moving momenta. Now, Gerard at Tufts is here somewhere. He was here. Oh, there he is. Now, he would say, well, use dimensional regularization. That's what you did with Veltman. But dimensional regularization is a great way of regularization, but it isn't really very physical as far as renormalization. That is, I mean, I still have to know that when I write G, I mean the physical G that is actually measured at large distances. So I have to relate what I'm doing, which I might regulate using dimensional regularization, to a physical G. Well, I guess I can do that, but I haven't done it yet.
So using a physical cutoff, but understanding how the energy momentum tensor is non-covariant in that physical cutoff, when you actually look at it carefully, the simple problems don't work out.
Well, okay. This is by certainly, since I'm somewhat stuck at this point, Anyone who wants to take this and run with it is welcome. Because I don't want to spend too much more on this. I tried to get as much done as possible for this meeting, and I thought it would be nice if I could talk about some work that's actually in progress rather than reminisce. Yes?
So your script R comes into your diagram. That's a scalar?
Yeah, that's a 3-scalar, not a 4-scalar. Yeah. Yeah, by the way, Maldacena calls it zeta, but he is wrong. I mean, in fact, there's a long literature on these conservation laws, and there are 2 well-known things which are equal outside the horizon but different inside the horizon. And all of his calculations refer to actually the thing that everyone else has always called script R, even though he calls it zeta, which is the name given to something else that's similar but not the same. So I reverted to the correct notation. Everything else in his paper is right. Yeah? Yeah, that's right. Okay. Everything's local. Yes?
Just a reminder, the in formalism that you
Yeah.
provide is exactly what Dalton and I with the PhD
Really?
called in the cutting walls. Dalton has written that
To Kutkovsky.
yes.
I remember you wrote papers in which you referred to the cutting rules, and certainly Kutkovsky wrote down cutting rules, but I thought that had to do with identifying singularities and Feynman amplitudes. But you actually used the in formalism for doing it? I don't think Kutkovsky did. Well, that's interesting because I...
The same thing in operators,
Yeah.
and the off-shelf.
Yeah, I'm so glad you said that.
Which means these diagrams that you need
Yeah.
to get unitarity.
That's fascinating, and I'll look back at your papers, but I'm glad you mentioned it because I didn't want to say this, but now I will, that I invented this formalism. And I was very proud of it, and that's what I was going to talk about, this lovely formalism. And then a graduate student said, there's something like this in a book by Bryce DeWitt, in section 31 of Bryce DeWitt's latest book, which unfortunately Bryce isn't with us now, but before he died, he finished this book called The Global Approach to Quantum Field Theory. And I looked at it, and indeed it is there, and it's originally due to Schwinger, before you or I were alert. No, well, Schwinger apparently was the first. What?
The condensed matter literature published is somewhat later, and it's known by a lot of people who use this to publish.
Yeah, and in fact, some people call it the Schwinger-Keldysh formalism. That's right. And one of the papers that I referred to was by Woodward and Sammis referred to it as the Schwinger-Keldysh formalism. But yeah, I thought it was fun to invent it, but no credit. Okay, thank you.